So hello guys, welcome to another episode of this exclusive tutorial. And last time we talked about the Carnot cycle, the processes involved, and we also solved some questions using the processes, and we also explained the graph, that is the TS graph, and how to relate it to the vapor tables, that is the steam table. Okay, now today we'll be looking at the Rankine cycle and also the difference between the Carnot cycle and the Rankine cycle. What is the major difference? Why is Carnot cycle not usually used in practice? So this is the reason. It's because Carnot cycle has a very low work ratio, and secondly, it has practical difficulty with compression. So what do we mean? If you look at the TS diagram we have here on the screen, you can see that at process 3 and 4, or from process 3 to process 4, is where we have the isentropic compression. So for a Carnot cycle, it is usually very small, smaller than the Rankine. So, and also it has a very work ratio, so nobody will want to use that or work with that. So literally, practically, we go with something that will yield more results, a better result, a better output. So hence the Rankine cycle. So now let's go to the processes in details. So process 1-2, okay, that is the expansive work. Process 2 to 3 is the constant pressure and temperature heat rejection. Constant temperature and pressure heat rejection. Process 3 to 4 is a compressive work. Then process 4 to 1 is none other than the constant pressure and temperature heat addition. Okay, now having noted this or having stated this, we go straight into the formulas, though most of the formulas we have stated them already in the Carnot cycle. So, but without mincing words, okay, without wasting much of our time, let's still go over it shortly. So we have the heat supplied. The heat supplied QS is given by H, that is H1 minus H4, then Q loss is H3 minus H2, turbine work, that is WT, the WT is equal to the H3 minus H2, and compressive work or pump work, which is WP is given by h4, no, h3 minus h4, or you can know h4 minus h3, right? Rather, h4 minus h3. So this is what we'll be using. Okay, now let's go down to solving a simple Rankine system, or let's go down to solving a simple Rankine question that will help us understand these processes far more better. So I go over here. The question. Now we have an example. Now example 1, calculate the cycle efficiency, the work ratio, the specific steam consumption of a Rankine cycle working between 30 to 0.04 bar. Now they say we should calculate. Alright, we are going to do just that. So firstly, remember, we start by writing our solution. So solution here, and our parameters given, though you don't have much of a parameter will be the graph. So we draw the graph. There is the TS diagram, and the TS diagram goes this way. TS diagram, we have it to be this. Alright, these are TS diagram. Our TS diagram is looking funny, so let's clean up this part and make it straight. Alright, yes, because it has to be straight. Okay, we have this. Good. So we have this. So remember our numbering: 1, 2, 3, and 4. Okay? Yes. So don't forget, S1 is equal to S2. Yes, S1 is equal to S2. But S3 is not equal to S4. Unlike that of the Carnot cycle. So we are given 30 bar and what? 0.04 bar. So what do we do here? What do we start working with? Now remember, just like I said, here is the saturated liquid line, and here is the saturated vapor line. Okay, and this superheated region, or superheat region. Okay, all right. Now, first thing to do is to grab your steam table. Get a hold of your steam table and go to 30 bar. 30 bar on your steam table. Now check the value of HF. Remember I said anything on the line, on this line here, as you can see 1 is on this other line, so anything on this line will have a subscript of G, okay, and this will have a subscript of F. So meaning parameters with subscript F are on the liquid that is saturated liquid line, and those with subscript G are on the saturated vapor line. So on your steam table, go to 30 bar on or from the steam table and the vapor table at 30 bar. At 30 bar, H1 will be equal to what? Hg, which is equal to 1008 kilojoules per kilogram. S1 is equal to Sg, which is equal to 6.186 kilojoules per kilogram Kelvin. Alright, but remember that S1 is equal to S2, which is equal to 6.186 kilojoule per kilogram Kelvin. Okay, that we have over here. So what do we do with that? How do we find the H2? So we first find the S2. We first find the X2, that is the dryness fraction that will enable us to find it. So from this formula, SFG, so S2 we have the value. So at 0.04 bar, you can see that at 2 the pressure dropped to 0.04 bar. So at that pressure, you go to the steam table, also go to that line, look at it very, very well, and get the value of SF. So from the steam table, the value of SF here is none other than 0.422 plus X2 into 8.051. So doing the maths, we have that X2 will be equal to 0.716 rather, 0.716. So with that, we can get our H2. Remember, H2, just like the S2, is given by HF plus X2 HFG, still at 0.04 bar. So H2, our HF is 121 plus 0.716 into 2433. That is HFG. So H2 finally is 1863 kilojoules per kilogram. Now the next is the H3. Well, you can see that the H3 is on the line, but which line is it lying on? It's lying on the saturated liquid line. So go to the table also. At 0.04 bar still, look for HF. Look for what? HF. So at P2 equal to P3, P equals 0.04. H3 is equal to HF, which is equal to what? 121 kilojoules per kilogram. Okay. Now, pump work. WP is given by H1, or rather, let's see it. Okay, H4 minus H3 given by what? H4 minus H3. Now, which is work? Alright, but what is work? Work is what? P dV. That is P change in V. Change in V. So it can also be, since this is a constant volume at compression, it's a constant volume process at compression, so the pressure changes. So you can see that the pressure is 2 at 30 bar and at 0.04 bar. So practically is going to change. So instead of having P dV, we have V dP. So we have this P1 minus P, yes, P4. So we can say P4 minus P3, right? Yes, because P1 is equal to P4. So P4 minus P3. They will bring this like. So P4 minus P3. Okay. Now H4 is VF P4 minus P3 plus H3. Okay, so the value of VF, you can get it from the table. If it's not in the table, it's not usually in the table, is 1 over the density of water, which is 1000. That will give us 0.001 into P4 is 30 minus P3 is 0.04, but remember it's in bar, so we convert to what? Kilopascal by dividing by 1000. So finally we have times 100 plus the H4. The H4 is the H3 rather is 121 kilojoule per kilogram. So doing this, we add that H4. This will give us none other than 2.99, if I'm correct. Let's punch it, check it on our calculator. So we have that 30 minus 0.04, okay, times 10. Okay, so we have here to be 2.996 plus 121 kilojoule per kilogram. So finally, this will give us H4 to be 123.996, which is equivalent to 124 kilojoule per kilogram. So we have gotten all our enthalpies. The next thing to do is to find the circle thermal efficiency, which we were told to find the work ratio and the SSC. Okay, so but before that, we have to find the heat supplies and the rest of them. So I'll open another layer. Okay, we have it over here. So he supplied will be equal to H1 minus H4, which will give us H1 is 2803 kilojoule per kilogram. Oh, that's right. Let's go back to our layer 2. Okay, now yes, at Takiba, our H1 was supposed to be Hg, but we took the value of Hf, so sorry about that. This is 2803. Yes, this is what it's supposed to be. Okay, that's what it's supposed to be. Now we should go back to what we were doing. So it's going to be this minus H4, which is 124. That will give us what? 2679 kilojoules per kilogram. That's the heat supply. So the next is the turbine work. Which is 12, that is H2 minus H1. Okay, the H2 we got was 186.3 minus H1, which is this, and give us 940 minus 940 kilojoules per kilogram. Okay, now what's the next thing? The next thing is the heat loss, which is given by H3 minus H2, which is, what was the H3 we got? H3 was 121 minus 121 minus H2 is 1863. So if you do that on your calculator, you have that Francis. If you do that, punch that on your calculator, you will have that 121 minus this. You have minus 1742 kilojoules per kilogram. Now the next on the line is work pump. Our work pump, remember, H4 minus H3, which give us 3 kilojoules per kilogram before. So as usual, we can cross check your network to know if it's the same. Okay, you can add, subtract heat supply for heat loss. It should be equal to the value of the change in turbine work and work pump. So network is given by W turbine minus W pump, which is 940 minus 3, that is 937 kilojoules per kilogram. So we go straight to the efficiency. The cycle thermal efficiency, which is network over heat supply times 1000 times 100%, sorry. So network is 937 over heat supplied is 2679 times 100%. So that will give us a network of a cycle thermal efficiency of 35%. Okay. The next is the work ratio. Work ratio, which is network over gross work, which will give us, the network is 937 over gross work, which is the turbine work. That will give us 0.997. The last but not the least, the specific steam consumption. Okay, sorry about that. The specific steam consumption, that is the SSC, specific steam consumption, which is given by 3600 over network, which has a value of 3600 over 937. SSC will be a value of 3.84 kilojoule. Now this should be kilogram per kilowatt hour. Alright, kilogram per kilowatt hour. Alright, yes, that's what we have. That's what we will have, kilogram per kilowatt hour. So now we have gotten everything asked in the question. The question says, estimate the cycle thermal efficiency, work ratio, and the specific steam consumption. As you can see here on the screen, we have achieved that. So we have solved an example to help illustrate the process. As you see this, you should know that it's the same thing as that of the Carnot circle. The only difference is that it has a bigger pump work compared to the Carnot circle, and it doesn't have same entropy. It doesn't have same entropy at the expansion and compression processes. So that's just the difference. So we have solved the question to help illustrate that. So with that, we have come to the end of this exclusive tutorial video. So stay tuned for more. See you next time and have a nice day.
It leads to liquor on some ladies. Yeah, we did turn up on a daily. It's how I walk up. Yeah, soft walk.